We symbolize it, I'll go into a fun color here. We symbolize it with the letter B, and that is kind of a random unit, a random variable, but it just is. The units for it are the units of what are called Teslas. That's where the famous name came from. So the name came from Nikolai Tesla, and he was actually one of the pioneers in the early, the late 1800s in terms of revolutionizing and innovating electricity and magnetism. We abbreviate that as a capital T. And there is a mathematical model that describes the magnetic field due to a moving charge, the magnetic field due to a current, which is a whole bunch of moving charges. But we are not going to get into the nuances of that magnetic field equation. But we do know that the strength of the magnetic field depends on the amount of moving charges. Strength of the magnetic field depends on the amount of moving charges how quickly the charges are moving, and the strength weakens the further away you get from the source. So the strength of a magnetic field weakens the further away you get from the source of magnetism. Okay, so now we're going to look at the magnetic field of moving charges.
Dear, you are not smart talking, okay?
So previously I was just looking at the magnetic field of permanent magnets, so things that we've taken ferromagnetic materials and we've created permanent magnets. Now we're looking at modeling the moving charges and the magnetic field associated with them, because that's innately where we see most of the magnetic fields in our lives. So usually a single electron has a pretty small magnetic field associated with it. But if you have a bunch of electrons, so if there is a current, so this is a lot of electrons collectively moving in a given direction. Then we notice a pretty large magnetic field associated with it. So there is a larger net magnetic field. And the magnetic field around a current is actually, they form these concentric circles, the magnetic field lines. So the magnetic field around a current forms concentric circles around the wire. And there is an equation that models this, but we are not going to look at the nuances of that mathematical equation. The physical model essentially looks at, and I'm going to draw a picture and then I'm going to show you a simulation. If I have a current, so here's my wire, and there's a current going through the wire. When I say that the magnetic field forms concentric circles around it, like the magnetic field lines physically like go around the wire and there are these concentric circles, so they kind of go outwards, and that's just at that point. Like, I mean, you could visualize it, and there's like here and here, and then you could, I mean, I could go crazy with colors here, right? And they just go further and further out from the wire. The magnetic field strength actually decreases the further away you get from the wire. But collectively they form these circles around the wire. And the direction at which they point, like I subtly put these arrowheads here, the direction at which they point is modeled using what's called right-hand rule number 1. And it physically shows how your finger wraps around the wire to show the direction of the current. Again, we are not going to go into the nuances of that because that's something pretty hard to describe and get you guys to practice without me physically being there with you. But I'll show a model that gives you the physical simulation of that so you can have a visual.
Okay, so in this video, we're going to see a wire connected to a battery and electrons are going to flow. It's actually modeling how the positive charges move. So the positive charges are moving through our wire, and this is showing how the magnetic goes around the wire. And the model shows that your right hand is wrapping around the wire and your thumb is actually pointing in the direction of the current. And then your fingers curl around in the direction of the magnetic field. And that helps us to visualize the magnetic field around a wire. Okay, so this is just another model with the iron filings. I can't do this model because I don't have a strong enough current to actually move the iron filings like I did with just my bar magnets. So I'm just relying on this simulation. So I have a bunch of iron filings on this little paper card, it says, and I've got this wire. And when I turn it on, then it's going to all of a sudden electrons are going to start moving through that wire, and that magnetic field, remember, around a wire, it forms these circles. You can see how the movement of the iron filings is showing that model of how they would move circularly or kind of arrange themselves in the direction of those magnetic fields. Okay, so this model, it's kind of a simulation, is showing how the magnetic field looks like around a wire that is carrying electrons. And so we know that anytime we have an electron moving, it's got a magnetic field around it or associated with it. And if you have a whole bunch of electrons moving, then you have a current. And so in this model, this current is traveling upwards, and you can see that the magnetic field is these circles around it. And so the kind of visual here, you can kind of see it's going around, and it's just showing this one spot, okay? And I can do a couple things. I can increase the current value, and if I increase the current value, then my magnetic field is going to get a lot stronger because collectively I have more electrons moving. More electrons means I have more individual magnetic moments that are contributing to the overall magnetic field. And then I'm going to bring it down to a more reasonable number. And then it's measuring the magnetic field at this like box right here, and I can actually move that box. So if I move that box further away, you can see that right here, this value here is showing me the Teslas, the magnetic field strength of at that particular point. So at this particular point, it's got, I don't know, it's a really cool simulation, but it's got really janky symbols here. I don't know why they can't just use a superscript or an E. But at this point right here, it's 4 times 10 to the negative 8 Teslas. So it's pretty weak. And if I increase my magnetic field, if I increase my current, you can see how that value goes up. Or if I move that point closer to my wire, then my magnetic field strength gets bigger and bigger and bigger. Okay, and to the point where like the biggest I can probably make it is if I get it 5 meters away from my object and I ramp up my current to be 20. Now, something to note as well is changing the direction of the current is not going to change the strength of the magnetic field. So I'm going to click on that button. But what did it do? Look at it again. It changed the direction of the magnetic field, okay? And that's going to be kind of important when we analyze a little bit later this concept of the magnetic field due to alternating current. So if I had alternating current, it'd be like, it's this direction, it's this direction, it's this direction, it's this direction. Like the magnetic field would be continually changing for alternating current as well. So kind of an interesting visual of the magnetic field around a wire.
So that's if you have just a single wire, and again, we're just having it big straight. But if you have a loop of wire, so this would be the magnetic field around a loop of wire. And this nuance is important because in everyday life, we see that it's beneficial to have a loop of wire because you end up getting a stronger magnetic field. And so what happens is if we take our straight wire here, and remember the magnetic field are these circles around it, and they go out further. And if we bend the loop, if we bend that wire, and instead we make it like go into a loop, right? And if in my model my current is like traveling in that direction like such, so my current is going to the right and through the loop and then back around, what ends up happening is a pretty cool effect in that the magnetic field ends up like circling around the wire like this. Let's see if I can. And you end up getting inside the loop actually a really strong magnetic field. Because if you could get another kind of visual of this, so if I slanted my view a little bit and change kind of the orientation, you end up getting that the field looks like this around. Boop. And so if you could just think about the inside of that loop and not so much worry about the outside, what ends up happening is you have this really, really strong magnetic field going inside that loop. And so we end up seeing that loops are really beneficial to creating stronger magnetic fields. So that's for a single loop.
Okay, so for this model, we're looking at taking our single like linear wire and looping it around into essentially a ring or a circle. And when you do that, you end up having a bunch of magnetic field lines in the center of your circle, and they add up to become a pretty strong magnetic field. And so if you were to increase the current that's going through the loop, then you increase the number of field lines inside here. You can see I can get more field lines. If I make the radius of my loop smaller, it actually concentrates them even more. So this is a way where we can create a pretty strong magnetic field. Ooh, there, it finally caught up. We can create a really strong magnetic field if we make our loop pretty small and increase the current through our loop. And in fact, that's just one loop. If you have a whole bunch of loops, then you end up getting an even stronger magnetic field down the center of your loop.
Now, if you have many loops of wire, so many loops, you have something called a solenoid. And so this is like taking my one long wire, and instead of it physically being linear, I take it and I curl it around like a giant slinky, right? And I take that huge length and I compress it into a smaller physical space by having lots and lots of loops. And remember that each loop, this is a terrible drawing, each loop has a magnetic field that's kind of like going inside, right? So think about this. What ends up happening is, golly, this is getting messy. I'm going to go highlighter mode here. You end up getting like this huge magnetic field down the center of this solenoid. And so in electronics, we often see that we have these solenoids, which a solenoid by itself is just a wire that contains lots and lots and lots of loops. And if I run a current through that solenoid, I end up having a really strong magnetic field down the center of that solenoid. And that's really beneficial in a lot of things in terms of electronics. So now I'm going to switch over and show you some simulations that kind of model the magnetic field of a solenoid, and then I'm going to show you some kind of fun applications of where we actually have solenoids in our everyday lives.
Okay, so again, I'm going to show a simulation that is modeling how the iron shavings behave if I have a current running through a wire, but this time I've got loops of wire, so you can kind of see how I've got this with a whole bunch of a single wire that has a whole bunch of turns or loops in it. And so my electricity is going to go through it. I'm going to create a magnetic field. Remember, when I have a loop of wire, I get a strong magnetic field inside. And if I have a whole bunch of loops of wire, I get a pretty strong magnetic field inside. So I go ahead and I turn that on. And you can see that I definitely have a lot of iron shavings kind of concentrated here as they go around this solenoid. So the magnetic field kind of model looks like this.